Hello everyone, my name is Tian Chunyang and my student number ID is MAT240925. Today we'll talk about the sequential characterization of continuity. So first let's talk about the theorem itself. The sequential characterization, so we need to use sequence. The function f is continuous at C if and only if for every sequence xn that converges to C. The sequence fxn converges to fc. So there are two important things I want to say. The first one is this theorem allows us to use the limit laws because this theorem involves the limit of sequence. The second one is this theorem will makes very easy for us to disapprove this function is continuous because we just need to find a bad sequence. The theorem is for every sequence, so we just need to find one bad sequence that not satisfy this theorem. This function is discontinuous. Yeah. So now let's prove this theorem first. Due to this theorem is if and only if theorem, so we need to prove from two sides. Now let's prove the forward direction. We assume f is continuous at C and we want to show xn approach to C imply that fxn approach to fc. So we let epsilon bigger than 0 and by the definition, so which is the epsilon delta definition, the continuous could imply that x minus c less than delta, there exists a delta bigger than 0, could imply that fx minus fc less than epsilon. So this is the definition of convergence. So that means xn approach to C, xn converges to C. And this also means limit xn equal to fc for epsilon bigger than 0. So this is our argument here. So we just show that xn goes to C imply that fxn goes to fc. So the forward direction done. Now let's prove the backward direction. For the backward direction, we'll use the contrapositive method. So we assume f is discontinuous. As I said, if you want to prove discontinuous, you just need to find one bad sequence, that's all. And we want to show there is a sequence. Yeah, we are finding the bad sequence. xn approach to C, but fxn not approach to fc. So here is a logic trick here. The theorem is xn approach to C imply that fxn approach to fc. So this is equivalent to not xn approach to C or fxn approach to fc. So due to this is a contrapositive, so we need to add a big not here. So these two are equivalent. This is the logic. Now let's prove. So we just need to define a bad sequence here. So exists epsilon 0 bigger than 0, and for every delta, we need to define that the delta is 1 over n. Why? Because 1 over n, when n goes to 0, when n goes to infinity, 1 over n will goes to 0. So the sequence we choose is xn minus c less than 1 over n, but fxn minus fc will always bigger or equal to epsilon 0. So by the Scream theorem, as I said before, this could imply xn goes to c because 1 over n goes to 0 when n goes to infinity. But as we defined, the distance, which is fxn minus fc, will always bigger or equal to epsilon 0. So this means fxn cannot converges to fc. So this distance cannot converges to 0. That is our argument. fxn cannot go to fc. So the backward direction will also die. Now let's see an example. The Thomas function. This function also named as popcorn function. This function defined on 0 to 1 open interval. So fx equal to 1 over q if x is rational number, which is p over q. And fx equal to 0 if x not in the rational number, which means irrational number. So the goal for us is to show that f is discontinuous at every rational number and continuous at every irrational number. So why we use sequential continuity here? Because if you use epsilon delta definition, it's pretty hard to show the discontinuous. It will involve the epsilon choose method. It's pretty hard for us. So we just find a bad sequence, as I said before, to show discontinuous. So now let's prove the discontinuity at rational number. So we just need to pick a C, any C, which in rational number set, and define fc equal to 1 over q. And definitely 1 over q is bigger than 0. So we can choose a sequence. We want to find a bad sequence, so we can choose anything. Now we choose a sequence of irrational number xn. So by the definition, fxn will always go to 0. By the way, for example, we could define xn equal to c plus square root of 2 over n. Yeah, so all xn will be the irrational number. So the limit of this sequence is 0 due to all fxn equal to 0. But the fc is not 0. The fc is 1 over q. So we could prove that limit of fxn is not equal to fc. We find that bad sequence. So we can prove that f is discontinuous at rational number c. So f is discontinuous at all the rational number. Now let's prove the continuity at irrational number. So we just to find irrational number c. So by the definition, fc is always 0. But we want to find any sequence, like all the sequence. When xn goes to c, the fxn goes to 0, which is fc. So there's only two types of number in the sequence. One is rational number, one is irrational number. So fxn is irrational number by the definition. Fxn will be 0. But what if xn is rational number? So let's define, for example, Pn over Qn. The denominator Qn. So here is a key argument here. So as n goes to infinity, Qn will also go infinity. Why? For example, we have 1.414. So x1 will be 14 over 10. x2 will be 141 over 100. x3 will be 1414 over 1000. So I know this is not the lowest term, but as you could see, when n grow up, the denominator 10, 100, 1000 goes very quickly. So when n goes to infinity, the Qn will also go to infinity. Therefore, the limit of fxn equal to the limit of 1 over Qn equal to 0. This is fc. So we have proved no matter the xn is rational number or irrational number, they all goes to 0. So fxn approach to fc for any sequence, no matter it's rational number or irrational number. So we just proved that f is continuous at c. So this is the Thomas function, and this is all my topic, the sequential characterization of continuity. Thank you for watching. I hope this video could help you. Thank you. Goodbye.